Hello, welcome to Getting Acquainted with Einthoven's Triangle, using the triangle to solve lead wire interchanges. I'm Dr. Jerry W. Jones. I'm the CEO and Chief Instructor at Medicus of Houston here in Houston, Texas. I also teach classes in London, United Kingdom. I have no financial disclosures. Most people reading 12-lead ECGs can easily recognize a fairly common right arm, left arm lead wire interchange by the inverted P wave in lead 1. Beyond that, however, it can appear quite complicated. Now, I've been using my own method for years, which has worked quite well, especially for lead switches other than the common right arm, left arm interchange. Now, before learning the Jones method, there are a few concepts you must be aware of. Before we proceed, now during this presentation, you may see or hear the electrode on the left lower extremity being referred to as LL or LF, left leg or left foot. Both are acceptable. The same goes for the ground wire lead on the right lower extremity, RL or RF, right leg or right foot. You may hear the terms lead wire switch, lead wire reversal, or lead wire interchange all mean exactly the same thing, and the terms are interchangeable. Are you tired of trying to remember which leads switch places? Are you tired of trying to memorize which leads change polarity and invert? Are you tired of trying to remember which leads switch places and invert? But most of all, are you tired of trying to visualize Einthoven triangles pivoting around in your head? This is a normal lead AVR. Now, lead AVR is going to be very important in the Jones method because we're going to be searching for lead AVR throughout all the augmented leads. The AVR lead can appear anywhere. It can appear in AVR as it's supposed to, but it can appear in the space for AVL or the space for AVF. So it's important that you can recognize lead AVR confidently. Now, in a normal lead AVR, you should have an inverted P wave, a primarily negative QRS complex. There might be a little tiny bit of an R prime as we see here in this tracing, but there may not be. If there is an R wave before the S wave, that would be distinctly abnormal. Now, what we're looking at here is a normal lead AVR. And of course, the T wave should be inverted. But like all other normal T waves, it will be asymmetrical, as is this one. A gradual downslope to the nadir of the T wave, then a more rapid, brusque return to the baseline. Now, does this look like lead AVR? Well, no, very obviously it doesn't. Or this. Well, we have a negative P wave, a primarily negative QRS, but we have an R wave appearing before the negative portion of the QRS. That is distinctly abnormal. And then, of course, we have an upright T wave. So no, this doesn't look anything like lead AVR should. Or this, we have an upright P wave, upright T wave. Even though we have an initially negative deflection in the QRS followed by an R wave. But this is not a typical lead AVR. Okay, how about this? Well, yes, here we have a negative P wave, a completely negative QRS complex, a QS wave basically, and then we have an asymmetric inverted T wave. So yes, this is lead AVR. It's actually lead AVR taken from a different tracing. Now, if lead AVR is not in its correct position on the ECG, then it can only be found in the space for lead AVL or lead AVF. The augmented leads, which are AVR, AVL, and AVF, cannot switch places with the standard leads, 1, 2, or lead 3. Let's take a look here. This is not lead AVR. Lead AVR cannot switch places with lead 1. It can only switch places with AVL and AVF. This is lead AVR. Okay, where is lead AVR? Well, there it is. Lead AVR, remember, is the right arm electrode. So we can say AVR or RA, right arm. Now, which lead has it switched with? It's switched with lead AVL, or the left arm electrode. AVL equals left arm electrode wire. So we have a situation where we have a left arm, right arm lead wire interchange. Now see how quick that was, and we didn't even have to look at lead 1. Okay, let's try another one real quick here. Where is lead AVR, the right arm electrode wire? Well, we find it in the space reserved for lead AVF, or the left foot or left leg. Now, which lead wire switches this? It's a right arm, left foot lead wire switch or interchange, sometimes called a right arm, left leg lead wire interchange. Same thing, same thing. And why do we call it that? Well, number one, the right arm electrode wire, which is lead AVR, is found in the space for lead AVF. AVF is the left foot electrode wire or left leg electrode wire. So the two have switched places. When we look up in the space for AVR, that's really AVF that we're seeing there. And we're seeing AVR in AVF space. So whichever space lead AVR appears in, other than its own space, that's the lead wire that it has switched with. So we have a right arm, left foot lead wire interchange. Now, here's a little problem here. This lead AVR has a little bit of an R wave that precedes the negative portion of the QRS. That's unusual. I would even say a little bit abnormal for lead AVR. But of the three augmented leads here, with the very obvious negative P wave, negative QRS, and asymmetrically negative T wave, the morphology we're seeing in AVF is definitely that of lead AVR. Now let's look at something else. When we look over in the standard leads, we see morphologies that could pass for lead AVR. In all of them, there is a negative P wave, a primarily negative QRS complex, and an asymmetrically negative T wave. The only issue here is that in leads 1 and 2, there's a tiny R wave, and in lead 3, the R wave follows the negative portion, so you have a QR morphology, whereas in 1 and 2, we have a small r, deep S morphology. However, these are not any kind of version of lead AVR. Augmented leads cannot switch places with standard leads. AVR could not have switched places with any of those leads, 1, 2, or 3, and vice versa. Standard leads cannot switch places with augmented leads. So what we're seeing in AVF is the true AVR-AVF switch, but not in 1, 2, and 3. Now, what happens when lead AVR is in its correct place? Well, when lead AVR is obviously located in its correct position on the ECG, we must look to the standard leads for help. Specifically, we must locate lead 2. Lead 2 is what's going to help us determine whether or not we have a true lead wire switch, a left arm, left leg switch, or simply a normal ECG. Well, what happens when lead AVR is actually in its correct place? Well, then we have to depend on lead 2 to help us decide if there is indeed a true left arm, left foot lead wire switch, or if it's simply a normal ECG. Now, remember, we have to find lead 2, which, like lead AVR, may or may not be in its usual space. What we look for is the standard lead with the largest P wave. We're going to be looking in leads 1, 2, and 3, and we're looking for the lead that will have the largest P wave. Well, here it is, and it's actually in lead 1. Now, if lead 2 has the largest P wave, then there is no lead wire interchange. But if lead 1 has the largest P wave, that means lead 2 has switched places with lead 1, which indicates a left arm, left foot lead wire switch. And that's the situation we have here. If we look over in the augmented leads, we see that lead AVR is in its proper location. But then when we look at the standard leads, leads 1, 2, and 3, we find that lead 1 has the largest P wave. Okay, that's not really lead 1, that's lead 2. Leads 1 and 2 have switched places. If we look down at lead 2, what we're really looking at is lead 1. So there is, in this case, a left arm, left foot lead wire switch. Okay, simply by following lead AVR, we can determine accurately, quickly, and quite easily 2 of the 3 lead wire interchanges not involving the ground wire, the right foot or right leg, which would be a left arm, right arm lead wire interchange, or a right arm, left foot lead wire interchange. The third lead wire interchange, in which lead AVR is located in its correct position, a left arm, left foot lead wire interchange, will require the location of lead 2, which we can identify by the fact that it will have the largest P wave of all the standard leads. If an interchange has indeed occurred, lead 2 will be found occupying lead 1's space. Otherwise, if lead 2 is in its rightful position, then no lead wire interchange has occurred. As I said in the beginning, the Jones method is to be used only with single lead wire interchanges that do not involve the ground wire on the right foot or leg. However, some of you may want more information on those lead wire interchanges, so I've attached a discussion with animations of those lead wire interchanges involving the ground wire at the end of this video. The overall video length hasn't changed much, but the portion regarding the Jones method is shorter and more concise, and the portion regarding ground wire interchanges is optional, having been placed at the end of the video. I want to thank you for spending time with me today, and I hope you learned how to recognize and determine a lead wire interchange with relative ease. Now, in the last screen, I'm going to tell you a little bit about the courses that I teach, and my contact information will be available to you there. My name is Dr. Jerry Jones. I'm the CEO and Chief Instructor for Medicus of Houston. Through Medicus of Houston, I am able to provide continuing medical education in the advanced interpretation of ECGs for physicians and other healthcare providers. From July 24th through July 27th of this year, 2023, I will be presenting the Master Class in Advanced Electrocardiography in San Antonio, Texas. The master classes last 4 days, from 8 a.m. until 5 p.m. each day. There's a maximum of just 20 participants in each class, sometimes even less than 20. The classes are very interactive and participatory. There are 14 hours of active participation by all in the diagnosis and analysis of complex electrocardiograms. The classes are very casual and relaxed, and participants may ask questions at any time. You do not have to wait until the end of a presentation. For more information, please visit the website posted on this page or email me via the Contact Us page of our website. I look forward to seeing you in one of the master classes very soon. We now come to single lead wire interchanges involving the ground wire, the electrode and wire on the right foot or right leg. Okay, let's talk a little bit about Einthoven's triangle. You'll notice that at each angle there is an electrode. We have the RA, right arm electrode, the LA, left arm electrode, and the LF, left foot electrode, which is also known as the left leg electrode. Now, there's also an electrode and wire on the right foot, or right leg if you wish. This is the ground wire. It does not record anything. The ground wire would have the same voltage as the left leg. So left leg equals RF. There is no difference in voltage. If we were to switch the electrodes with their wires, put the left one on the right foot and the right one on the left foot, you would not be able to see any difference in the ECG tracing. Okay, we're going to talk a bit about a lead wire interchange that involves the right leg or right foot. And what's unique about this is that the right foot is the ground wire, the neutral wire. We don't normally record anything from the right foot. It's there as a reference point. Now let's look at the electrodes as we have them attached. Right arm, left foot, and right foot. I've outlined the right foot in blue. And we're going to switch the right foot and right arm electrodes. Okay, now which lead is defined by the left foot minus the right arm, by AVF minus AVR? Well, lead 2 is the lead that is defined by that. But where is the right arm located now? It's located on the right foot, isn't it? So what's the significance of that? Well, as you recall from very early in this presentation, the left foot and the right foot record the same voltage. So now the left foot minus the right arm, which is on the right foot now, equals 0. Left foot minus right arm equals 0. So how will you recognize this on the ECG? Very easily. Lead 2 will record an isoelectric or near isoelectric baseline. Now here is a recording of someone who has had their right arm and right foot lead wires switched. And as you can see in lead 2, it's nearly totally flat. Not absolutely flat, but almost totally flat. And it's unlikely to see this in lead 2 anywhere else other than a right arm, right foot lead wire switch. Okay, by the way, FYI, it really doesn't matter which lead is on which foot. They will both have the same voltage, and one subtracted from the other will still produce the same result, 0. Okay, now we're going to talk about a lead wire switch involving the left arm with the right foot. So here are our electrodes, and we do the switch. So which lead now is defined by the left foot minus the left arm? Well, that's lead 3. Lead 3. It runs between AVF and AVL. But where is the left arm located now? Well, it's on the right foot. And what's the significance of that? As before, the left foot and the right foot record the same voltage. So now the left foot minus the voltage of the left arm, which is really on the right foot, equals 0. Left foot minus left arm in this case equals 0. So how will you recognize this on the ECG? Again, very easily. Lead 3 will record an isoelectric baseline. Here is an example of a person with a left arm, right foot lead wire interchange. If you look down in lead 3, it looks just like the lead 2 we saw before. It has basically a flat baseline near isoelectric, and you're not going to see much of anything else causing that in lead 3. Okay, so we saw a lead wire interchange that resulted in an isoelectric baseline in lead 2, and then we saw another lead wire interchange, a single lead wire interchange that resulted in a near isoelectric baseline in lead 3. But what about 1? What about lead 1? That's actually going to take a double lead wire interchange to get the same type of baseline in lead 1. So we're going to talk about a double lead wire interchange, which includes the ground wire. Okay, we're going to talk about a double lead wire switch involving the ground wire. What we're trying to do is to get an isoelectric baseline in lead 1, and this is how it happens. First, we look at our electrodes. Now, a double lead wire switch is going to be the right arm changing with the right foot and the left arm changing with the left foot. So here we go. Okay. Now, which lead is defined by the left arm minus the right arm? Well, that's lead 1. But where is the left arm located now? It's located on the left foot. Where is the right arm located now? Well, it's located on the right foot. And remember, the left foot and the right foot record the same voltage. So now the left arm minus the right arm, which is really on the right foot, equals 0. Left arm minus right arm equals 0. How will you recognize this? Very easily. Lead 1 will record an isoelectric baseline. Okay, to get an isoelectric baseline in lead 1, as we see here, both the right arm and left arm wires must be on the feet. It really doesn't matter which foot the lead wires occupy, actually. The same result with either wire on either foot. But wait, there's more. There's actually another way to get the isoelectric baseline in lead 1. So we're going to have a right arm left foot interchange along with a left arm right foot lead wire switch. So here we go. So the end result of this crisscross lead wire interchange is that the right arm wire and the left arm wire finish by being located on the feet. You'll notice now they're on opposite feet than they were previously. But since they now have the same voltage, they're going to cancel each other, resulting in 0 voltage, and an isoelectric baseline will result in lead 1. Again, it doesn't matter which foot they occupy, the result will be the same, 0 voltage. Now, I want you to be very careful if you do see a near isoelectric baseline in lead 1, because a double lead wire interchange is not the only phenomenon that can cause a near isoelectric baseline in lead 1. Advanced COPD can do that, especially advanced emphysema. A mean QRS axis in the frontal plane equal to plus 90 degrees could do it, and a mean QRS axis in the frontal plane of minus 90 degrees could do it. However, advanced COPD is a lot more common than a double lead wire interchange. So here is a checklist of 4 things to look for if you're trying to determine whether a lead wire reversal or interchange is present. If the P wave in lead 1 is upright, you check to see if the P wave in lead 2 is upright and taller than the P in leads 1 and 3. Leads 1, 2, and 3 are not isoelectric, and lead AVR is located correctly in its own space on the ECG. If you find all these things to be true, then there are no lead wire interchanges.